Hi, welcome back. In this lecture, I want to talk about the output of quantum neural network, which will be our measurement of the quantum computer system. In quantum neural networks, the output used to compute the loss function comes from the quantum system measurement. In order to understand the output of quantum neural networks, in this lecture, I want to define two things. First, what is an observable of a quantum system, and what is the expectation value of an unobservable. The goal of this lecture is to connect the standard quantum mechanics picture of the measurement to quantum neural network output and to the definition of losses in our quantum neural network. What are physical observable? Well, in quantum mechanics, a physical observable, such as energy, spin, parity, is a quantity we actually can measure, and most importantly, is represented by an Hermitian operator M. So M is a matrix and it will have the properties of being Hermitian. So this is extremely important. Associated with the Hermitian operator M, we have two major outcomes. The first one are the eigenvalues of M, which are the possible measurement outcomes of the measurement of the observable M. So we take our observable M, which is represented by a matrix M, which is Hermitian. So M equal to the joint of M, which also support a matrix representation. One outcome will be the eigenvalues of this matrix, which are the measurement possible outcomes of this observable. The second outcome of this Hermitian observable are the eigenvector associated with the eigenvalues. And these are just the post-measurement state. The states the system collapse to after measurement. For one qubit, we often use a simple 2 times 2 matrices, either defined as a projectors or a polymatrices, and this will be our observable. In quantum neural networks, this observable will define what quantity we read out from the circuit to feed into the loss. What it means to measure a qubit in the computational basis? Well, we need first to associate the observable, which are Hermitian matrices. For instance, we can represent two matrices M and matrices Z. So in this case, it's just a projector, and this is a poly Z type observable. So we start from the basis state. The results of our measurement will be collapsed to one of these two states, either state 0 here or state 1 here. There are two standard observable for a single qubit. The first one is a projector type observable with eigenvalue either 1 and 0, respectively for state 0 and 1. We can also have a poly Z type observable with eigenvalues +1 and -1. Both these observable measurement corresponds to measuring in the computational basis, but assign different numeric values to the outcomes. In quantum neural networks, we choose a convention, either output between 0 and 1 or output between -1 and +1, which will suit our loss function. The second important concept in this lecture is the expectation value associated with an observable. The expectation value is often indicated as the symbol of the matrix that represent the observable between this angle bracket here. So let's have a qubit in the state defined by amplitude A and B for state 0 and 1. Measuring an observable gives a random outcomes M, for instance, can be either 0 or 1, or it can be -1 and +1, depending on the observable. Remember, the observable outcomes are just the eigenvalues of the Hermitian matrices. And these random outcomes are given by probability determined by psi. The expectation value is formally defined as the sum over the possible outcomes. In the case of a one qubit, we can have only two outcomes, either 0 or 1. So M will go across 0 and 1. And expectation value is just the sum of the possible outcome, it is 1 multiplied by the probability. For instance, if we have another AND gate acting on the state 0, so the expectation value for a projector type where we can have outcome 0 and 1 will be nothing else than 0 multiplied by 1 over LF plus 1 multiplied by 1 over 2. So the expectation value will be 0.5. We can also have a bracket notation for the expectation value of an observable M represented in the following way. So we apply our matrix corresponding to the observable to the quantum state, and then we take the inner product of the resulting state from this first operation with the state psi. What is the intuition of the expectation value? Well, the expectation value of an observable M is the average measurement results if we repeat the experiment many times. In QNN, the expectation value is often equal to the model's output, yx of theta. So we will take this expectation value as the output in order to calculate the loss function. In this slide, I just provide a very simple example how to compute the expected value of M in a 1-qubit system. So we have a generic quantum state psi with amplitude alpha and b, and then we have a matrix representation of our observable, and we'll have this matrix also need to be Hermitian. In order to calculate the expected value, we apply two steps. We first calculate the V, applying the matrix M corresponding to our observable to the quantum state. And this corresponds to a matrix vector product. And then we compute the last step, that we take this output and we calculate the inner product with the psi. So this is just row column product. In example for a poly Z observable, where we have possible outcomes of 1 and minus 1, and we calculate the expected value from a quantum state where the probability to measure is 0 and 1 is the state is the same after the measurement, then this will give an expected values of 0. Remember, this is poly Z, the two eigenvalues are +1 and -1. In the case of a projector, then this will give 0.5, as I mentioned in the when discussing the previous slide. We can generalize this to multi-qubit observable. So what we're going to do is just to build a tensor product of these matrices and then apply in the very same way to our quantum system that in this case will be a multi-qubit system. The PennyLane framework allow us to do this in a very nice and a straightforward way. We can just call a function called xval for expectation value, and then we need to tell which observable and in which qubit. In a quantum neural network, we choose such an expectation value, so then this can feed in the output of the quantum neural network. And the model will use this output to calculate the loss. Quite important observable is the so-called parity observable. I already discussed a little bit about the concepts of a parity. Given a bit string, we basically count the number of 1, and then we say if it's even and odd. It turns out that we can build such a parity observable by considering a tensor product of poly Z gates. So for instance, for 2 qubits, you can just take this tensor product and apply. In matrix form, P is 2 times 2 to the n times 2 to the n diagonal matrix with entries +1 or -1, depending on the parity of each basis state. The important part is really the expectation value of such a parity observable, which is equals to the probability of even parity minus the probability of odd parity. In a QNN, to choose the parity observable as an outcome of our neural network means that we take it as a measure up, and we take it as a global feature summarize even odd structure in the output distribution. So typically what you can do is to take expectation value of a certain qubit. This will be kind of local measurement of your quantum system. Instead, if we want to have a global picture of the full distribution of our quantum state, we can use the parity observable. In a QLN, we choose an observable M and define the module output taking this observable. So for binary classification, a common choice is to take Z on qubit as observable, and this will give values between -1 and +1 as the outcome of the measurement. We can then map it to a probability just applying a simple transformation as in this slide. Given then a target label T, for instance, as a supervised training, we can then define a loss function in a different way. We're just taking the difference of our outcome from the label and calculate the loss. Remember that the training loop, we run the circuit, we estimate the expected value, we compute the loss, and then we give this loss function to the classical optimizer to calculate the new theta to give to the variational form circuit. This is the last slide of this lecture. Talk to you soon.